So we're going to continue talking about definite integrals, about finding the area under the curve. We may throw a little Riemann sum in here. But I would like to continue by talking about still how the integral is the area under the curve, but we can find it using different methods if we are clever. And that's probably the most important thing that you should be in physics is clever, which means you kind of look around and notice what's going on. All right, so let's see if we can notice what's going on with page 287, number 13. If somebody would read it for us, please. Yes, you did. Very good. Okay. So remember that this part here is the integrand, which means that's the function that we are taking the integral over. That is the function that we are taking the area of between that function and the x-axis. And then we have our limits, -2 to 4, that tells us what the vertical boundaries are. And we'll talk about what that means in a minute. So for these exercises, we are specifically supposed to use the graph and the area under the graph to find the integral. So what is this a graph of? What kind of function is the integrand? So it's a straight line. Okay, so let's plot up this straight line from -2 to 4. 1, 2, 1, 2, 3, 4. And since we know it's a straight line, I really only have to plot a couple of points, right? So I would probably plot my endpoints. So for instance, if x is equal to negative, well, let's do it this way. Let's be a little formal here. Let's say f of x is equal to x over 2 plus 3. So on the left-hand side, f of -2 is going to give us what? 2. Okay, so that's going to be about here. The y-intercept's always a good thing to find. So what's f of 0 going to be? What is it, Gianni? 3. Good. And then let's look at our upper limit at x equals 4. And what do we get? 5. Okay, so this is going to be a straight line. And if I'm finding the area under the curve, it's going to look like this. And what is that? It's a trapezoid. So we basically, or let's write it this way, the integral, which is the area under the curve, is the area of the trapezoid. Anybody remember what the area of a trapezoid is? Excellent. well, yeah, let's identify on our graph here. So this is going to be B1, because remember the bases are the sides that are parallel. This, even though it doesn't look parallel, is going to be B2. And then that distance between the bases is going to be H, which is going to be 6. Okay, so we can substitute in here, and we've got 1/2. We said the base, we said the height was 6. B1 is f of -2, which we already figured out to be 2. And B2 is going to be f of 4, which we already figured out to be 5. So what are we going to get for the area here? 21. Okay. If they had given you units, you would need to write like meters squared or whatever the units are. You can, but your calculus book and calculus in general has a very loose relationship with units. Yeah, it's kind of annoying. I don't think it's written by a math teacher, not a science person, which is wrong. But calculus was invented so we could do physics. It's a tool. Yes, I would say that the integral, so you could say, if you wanted to take it that one step farther, that the integral from -2 to 4 of x over 2 plus 3 dx is equal to 21. Okay. The area should be the same no matter how you find it. Right now, we're finding the area by, we could use Riemann sums, we could use that RAM program, we could use the area under the curve if we can figure it out another way. As we get farther along, we'll be finding the integral using antiderivatives. You can find it however you need to find it, unless the problem says do this a specific way. And sometimes I want to make sure you know how to do it a specific way. And sometimes the AP exam wants to know that you can do it a specific way. Okay? So let's talk about negative area. And all negative area means is that it's area below the x-axis. So if I have some line here, which I believe is y is equal to -x, I could be wrong. And I want to take the integral of -x dx from 1 to 4. So I'm going to take it from here to here. Because that area is below the x-axis, that integral is going to have a value less than 0. Now this becomes important mostly in physics applications. AP Physics people, what is the #1 application that we have used finding the area under the curve for? Work. Okay, where work is equal to the area under the curve. Well, if instead I wanted to find the integral here from -2 to 2, and my force is for some reason -x, so now I've got this area and this area. What's the amount of work that's going to be done be equal to? 0. And it just means that I've put, work is the transfer of energy. It just means that I've put in as much energy as I've taken out. Okay? If my work was this, my original integral from 1 to 4, it would mean that I'm putting energy into it as opposed to getting energy out of my system. I'm pushing the block up the incline instead of letting the block slide down the incline and releasing energy. Okay. All right, we good? Okay, so I'd like to go over exploration 1 because it really kind of talks about this whole kind of negative area thing, and it's pretty useful. It actually brings together a whole bunch of stuff. So, exploration 1 tells us that the integral from 0 to pi of sine x dx is equal to what? 2. Okay. And so we could plot that because we know that from 0 to pi, a sine curve looks like this. And up here will be 1. So this tells me that this area here is equal to 2. Okay. Now this is pretty powerful and pretty important because this shape here repeats itself all the time. It will repeat itself within the sine function, right? Because you know that the sine function is going to continue like this. It also appears in the cosine function. So anytime I see that shape, I know that I have an area of 2. So let's do a bunch of these. Okay, so the first thing that you're supposed to look at in number 1 is the integral from pi to 2 pi of sine x dx. So let's graph that again. Right? My sine curve starts like this, goes like this. So here's going to be pi, here's going to be 2 pi, here's going to be 1, here's going to be negative 1. So what area am I interested in finding this time? Yeah, over here. Hang on. It should be negative 2. It's the same shape as we had up here, and we know that that area is equal to 2. But now, like we just talked about with negative area, because it is below the x-axis, it's going to be the same amount of area, but it's going to be negative. So the integral from pi to 2 pi of sine x dx is going to be equal to negative 2. All right, we good? All right. So how about number 2? What does that ask us for? Okay. So that's going to be this whole part of the curve. Now, as we'll learn, what you can do is you can break this integral up. Okay, I can break this into an integral that goes from 0 to pi, of sine x dx plus an integral from pi to 2 pi of sine x dx. And as long as the upper limit of this integral is the same as the lower limit of that integral, I can break it out. Okay? Sometimes we do that for geometry's sake, because maybe one part of the curve is a straight line and the next part is a horizontal line, and it makes it easier for me to figure out the area. Here I'm doing it because from 0 to pi I have a positive area, from pi to 2 pi I have a negative area. As you should have read about, we might also do this if we have a discontinuity. Okay, so what's the area of the integral from 0 to pi of sine x dx? 2. And then what's my integral from pi to 2 pi of sine x of x dx? -2, so my area is 0 because I have the same amount of area above and below the curve, and they cancel each other out. How about number 3? What does number 3 ask us for? Zero to what? Still my sine x dx. So now I want that area because this is going to be halfway through and it'll be pi over 2. So what do you think the integral is going to be? 1. It's going to be half of 2 because I'm only using half of that nice symmetric curve. Okay. How about number 4? What does number 4 want us to do? The integral of what? Okay. Now, the integration operator, or the integral operator, distributes. So I can really write this as the integral from 0 to pi of 2 dx plus the integral from 0 to pi of sine x dx. Okay. I know what this is, right? So we're not going to worry about that for the moment. That was defined at the beginning. But this part here is the integral of a constant. And what does theorem 2 tell us about the integral of a constant? It's equal to the constant times the upper limit minus the lower limit. Okay? And then what's the integral from 0 to pi of sine x dx? 2. Okay? So my answer is 2 pi plus 2. You can also think about this first integral as a rectangle. Y equals 2, right? That's what the line would look like if I consider this to be my integrand. And then I'm just going to take the area from 0 to pi. And that would give me the area of a rectangle. And what's the area of a rectangle? Base times height, so that would give me 2 pi. So it's not magic, it's just math. All right, we good? All right, did everybody get these? Am I boring you because you got them all and you understood everything you were supposed to understand? Let's keep going. Okay. Number 5, what's number 5? Okay, so I'm pretty sure that another one of those things from Theorem 2 tells me that when I have a constant, I can bring it outside the integral. So I can call this 2 times the integral from 0 to pi of sine x dx. So I just kind of keep my 2 out front, and then what's the integral from 0 to pi of sine of x dx? 2. So what's my answer here? 4. All right. Number 6 gets nasty. So number 6 is the integral of 2 to pi plus 2 of the sine of x minus 2 dx. Or at least it looks nasty. Yeah. But it's a card thing. It can be kind of wacky. So let's talk about this for a minute. Okay? So if I'm going to plot sine of x minus 2, that shifts my sine curve, right? Which way does it shift it? To the right. So that means that whatever I would have had at 0, I now have at 2. Okay, so then I'm going to go like this. And this should be 2 plus pi. Does that make sense? Yes? Okay. So that's my familiar shape that I know the area of, or the area under. But then, as Zoe pointed out, I've also shifted my limits. So I'm taking the integral of that same part of the curve as I've been taking all along. It's just that I've shifted the graph, I've shifted my integrand, and I've shifted my limits, so no matter what, I'm still going to get 2. I think it looks nasty and scary when you first look at it. Okay, we got it? All right, number 7. What's number 7? Somebody other than Zoe. Just read it to me. Sari, what is it? du. Okay. So remember yesterday that we were talking about dummy variables. Here's a dummy variable. It doesn't matter what my variable of integration is, as long as the variable in my integrand, which is u, is the same variable in my d whatever. Okay, so this is the same thing as writing the integral from negative pi to pi of sine x dx. It's the same thing. And again, if I want, I can break it down to the integral from negative pi to 0 of sine u du plus the integral from 0 to pi of sine u du. And you just might want to do that so that you can separate out the positive area and the negative area. Because, of course, if you graph this, over here from 0 to pi, you're going to be below the axis. I'm sorry, from negative pi to 0, you're going to be below the axis, and from 0 to pi, you're going to be above the axis. And so what do we get for our answer? 0. What kind of a function is sine? It is cyclic. That wasn't quite what I was going for. It's an odd function. What do you notice? It is a trigonometric function as well, but odd was what I was going for. What do you notice about the integral? It's 0. What was that other?
So does that mean for the integral is 0?
Right, this was an odd function too, right? What was that? Yes. If it's an, pardon me? No, it doesn't even have to be a whole period. If it's an odd function and you take equal chunks on either side of x equals 0, you have to, by definition, get 0. Interesting, isn't it? Remember that I said this. It'll come back later. All right, what are we on to here? Number 8? Gianni, what's number 8? There we go. All right. So what's that going to do? What does that do when I graph it? Okay, so Maddie says it stretches out. So now my first arc is going to go to 2 pi. But what's the area of the arc? What? I have 4 written down. Well, that's not going to work. Oh, no, it shouldn't. What did I do wrong? That's 1/2. The antiderivative of cosine is negative sine. Oh, because I didn't put it back in. That's what I did wrong. So that's going to give me the cosine of pi, which is -1, minus the cosine of 0, which is 1. No. Well, let's do this. You can also figure out areas with your calculator, right? So if you go to Math 9, It's FNINT. Oh, okay. And the way that you put it in, so you've got FNINT. Some of you will have really crazy, wacky stuff. Okay. So you're going to put in your function, which is going to be sine x over 2. You're going to put in a comma. You have an actual comma button on your calculator. You need to use your comma if you're doing it the old-fashioned way. You need to tell it what variable you're going to integrate with respect to, which is x. And then you're going to give the limits. And you close your parentheses and you hit enter. Pardon me? It depends if you have an, yes, if you have that slightly newer calculator. I don't know, Zoe. You'll have to figure it out. Oh, you have an answer? Cool. What's your answer? Well, because sometimes she's got that funky calculator, and then I have to. It's not that mean. Was I? I'm sorry.
One day, Dr. Montgomery was like, because 1 plus 1 is 2.
I try not to. Where is? What'd you get, Zoe? Did you get 4? Are you in radian mode or degree mode? You need to be in radian mode.
I got 4. Wait, I'm in radians and I got 4.
You should be in radian mode because this is calculus. I don't, it's ridiculous and I should not say it, but that whole stretching and that whole thing when you manipulate trig functions like that always messes me up because I don't have to do it. And I was trying to do it by hand and I didn't. So the answer's 4. And we did the other example I wanted to do. So we're good. What this actually does, this numerical integration, is it actually finds the Riemann sum. But it keeps finding it for a bigger and a bigger number of subintervals. So it's really using RAM, but it makes n be larger and larger and larger until LRAM, MRAM, and RRAM converge and agree to a certain number of decimal places. Because that was easy. It was a trig function. We could give it something harder and it would take longer. All right, so let's finish up these last couple here. So number 9 mixes it up a little bit because it's the integral from 0 to pi of cosine x dx. So we probably want to graph that. And remember that cosine x from 0 to pi is going to look like that. And here's going to be pi, and here's going to be pi over 2. And the area that we look for, or that we're calculating, looks like that. It is going to be 0 because you've got half of one of those bubbles or peaks above the x-axis and half of one of them below the x-axis. Okay. We good? And number 10 says suppose we have any constant k, it's a positive number, and we're going to take the integral from negative k to positive k of sine x dx. We just talked about this. What is that going to be equal to? 0. Okay, because why? Yeah, because sine x is odd, and I don't know, we're taking and our lower and upper limits are equidistant from x equals 0, because that's part of it too. If you're not taking a symmetrical interval, you can't go from like negative k to positive 2k and get 0. It's got to be that you're at the same thing. Okay? All right, so I think the bell's going to ring, and we will end here.